Okay, so good evening, students. This is Dr. Dong. Today I'm going to record the video on virtual memory. Last week we mainly focused on the topic of main memory, but this week we're going to move on to virtual memory. So here, the biggest question or the first thing that I want to explain before stepping into the details of virtual memory is the difference between virtual and physical memory or main memory. So from physical and main memory, you can tell it from the name. Okay, so it is just the RAM. Okay, so it just gives you the idea of how is our physical RAM organized. With previously we said that we usually divide the very large space, the RAM space, into different pages, a lot of pages. Each page usually is around 2 KB or 4 KB or as large as 1 megabytes. So the main memory or physical memory mainly refers to the thing. Okay, so how is our what kind of thing is stored in the physical memory? But the virtual memory is something that is really virtual. Okay, so it is our imagination of the memory, or it is an abstraction of the physical RAM. So the physical RAM is the management of physical RAM is more complicated. And whereas the virtual memory is just our imagination. You can take it in this way. Okay, physical memory is pretty much like the physical gears on your vehicle's transmission. So it's really complicated, and we don't know how to handle that. But what is virtual memory? Virtual memory is like the transmission stick. Okay, so you know that if you turn it forward, it will step into the next gear. If you move it backward, it will go to the lower gear, go to a lower gear. This is an abstract transmission stick. Okay, this is an abstraction of those very complicated physical parts of your car. And so for us, the programmers, we just need to focus on we just need to imagine. Okay, so we just need to imagine the virtual memory, worry about the virtual memory, whereas we leave the manipulation of the physical memory to operating systems. So it's a big relief for programmers like us. And last week, this is the picture that shows what we have learned from last week. We said that there is a hardware called MMU, memory mapping unit, which is responsible for us to translate between logical address or virtual address to physical address. So it's like this is the address in your imagination, and what is the address that is actually in your physical memory in reality. And so we learned two different ways of allocation of physical memory space allocation, which are contiguous and allocation and uncontiguous allocation. For uncontiguous allocation, this one is definitely more popular because it has a better utilization rate of our physical memory space. And we talk about paging. It's like we divide a very large space into different pages, and each page is like the unit for us to do allocation. And then we learned another concept named segmentation. So today we're going to learn physical memory, and this is the list of topics that we are going to talk about. First, let's have a background. Why should we to know why should we have virtual memory? Okay, so suppose like this, we only have a very small RAM. So you only have a very small RAM, say 8 GB, and now you want to play a game. You want to play a video game, and this game is really huge. Let's say it is 30 GB. And then so previously we said that in order for us to execute a program, we have to load this program into the RAM first. But the problem over here is that the program itself is larger than the whole memory space, so we cannot afford to load it. Okay, so then this is one reason why we have virtual memory. With virtual memory, we can just imagine that, okay, every line of the program has been loaded into the physical memory, but actually it is not. So it provides an abstraction for us, or an imagination such that everything is loaded into memory. And then so the other reason for us to use virtual memory is this. Okay, here I just take a screenshot of the manual for the command ls. So ls is used to list the all the files or folders, subfolders included in a certain folder or directory. So these are the very different. There are a lot of options, like -l, -a, capital A, little a, capital B. So each of them is like a variation of the program of the ls command. For example, if you use ls -l, it will list every detail, all the details about the files. So, but we rarely use them. So here is the thing. Okay, when you are developing a program, you want the program to be very comprehensive, so you give a lot of operations, you provide a lot of options for the users to use. But the thing is that in reality, most users just going to use the most fundamental or the most simple option, or with no option. Most people will just use ls without any option, so which makes the code, the program for these options, not used for most of the time. So for those parts that are rarely used, it's not. So if we're not going to use it, then why should we load them into memory? Because if we want to copy those things and that we rarely use into memory, it also takes time, right? It not only waste the memory space, but it also wastes your time. So with virtual memory, okay, we are pretty fine with first imagining that everything is inside the physical memory, but actually the rarely used part of the whole program is still left in the hard drive without being copied into the physical memory. And this saves our memory space as well as the time. So this is the benefit of using virtual memory. Okay, and also the benefit of having the ability to execute a program that is partially loaded into memory. So first, there is no program size limit, and so that more programs can be executed at the same time. And then we got less input and output time used for swapping. So for swapping files from the disk to from the hard drive to the memory, and from the memory to the hard drive. And so here is the virtual memory. Okay, so virtual memory involves the separation of logical memory as perceived by users from physical memory. So it provides a separation or abstraction of the physical memory. So and also it provides the ability to execute a program that is only partially in the physical memory. So and for us the most significant benefit is this. Okay, so we don't need to worry about the amount of available physical memory space, and also we can just assume that we have infinity physical memory space, and everything that we need has already been loaded into the physical memory. But actually in practice they're not. So in case that we want to, so we need a specific line in our program, so the operating system is going to be responsible for to load it into the physical memory. And so this is the what we learned last week. So on the left we have the virtual memory. So the virtual memory is in virtual memory we have a lot of pages, and whereas in the physical memory the number of pages is smaller. So then we need the memory mapping unit to tell us, okay, so page X, virtual page X is stored at physical page Y. So we say that the memory mapping unit is pretty much like a translator to help us to translate the page number from between virtual memory space to physical memory space. And then this is the picture that we have seen a lot of times. That is the process space in our memory. And so let's consider this. Okay, so suppose that we have a program that is this huge, but and our physical memory is very small. So actually a part of the pages, like the pages in red colors, are still stored in the hard drive, whereas with the help of virtual memory, we can pretend that everything has already been loaded into the physical memory, but actually they're not, because only those pages with green colors are in the physical memory, whereas those pages with the red color are still in the hard drive. So for us, the programmers, we can pretend that everything is in the physical memory, and we can leave the manipulation of physical memory alone. And believe me, that this is a huge relief. So if you are doing assembly, if you're doing programming in assembly or in like the very early version of C, you have to keep track of everything. Okay, you just create an array, and you need to know where is this array stored in your physical memory, and it's really complicated for us to do the programming, and so nobody likes it. And then and another thing is that with virtual memory, we are allowed to share pages between two different processes. And previously we learned the concept of shared memory between two processes. Okay, so and the next concept that I need to talk about is demand paging. Demand paging is this. Okay, giving the problem is that, okay, if we have a program with a lot of options like the ls command, so the first option is that we load the entire program into the memory. The second option is that we only load the necessary part first, and then if just in case that an option is called by the user, then we load that part, and this is called demand paging. Okay, so with in modern operating systems, we always choose the second option because because of the reasons that we talked before. It allows the execution of programs whose size is larger, and then so this is called demand paging. So say when we are executing a program, just in case that we want to say we just finish executing the instructions in these pages which have already been loaded into memory, we swap them out and bring in some new pages from the hard drive for future execution. So this is called demand paging, and a swap between the hard drive and the physical memory is called a page fault, which we are going to talk about later. And so from the perspective of operating system, so a very important task is to keep track, okay, which virtual page is in the physical memory and which is not. So that is why in the page table, so in the page table, we associate each page with a bit. So this bit can be either V or I. V stand, or you can take it as 0 or 1. So V stands for valid, meaning that this page is in memory. I stands for invalid, meaning that this page is not in memory. So here is one example. So this is our logical memory or virtual memory space, virtual memory, and then this is the page table. So in the virtual memory we have 8 pages. So then the page table also includes 8 pages. Also includes 8 entries. Okay, each entry corresponds to one virtual page or logical page, and then so this is our physical memory space. From here we can see that only ACF, which are the zeros, second, and and also the fifth page are in the physical memory, whereas all the other pages are on the hard drive. So that's why in the page table we have V for the page 0, page 2, and page 5, and then we have I for all the other pages. Okay, so if we want to visit a page which is associated with a invalid bit, then we say there is a page fault. A page fault means that you want to access a page that is not currently in the physical memory space. And then so in case that there is a page fault, what we need to do is that we need to read the page from the hard drive to the memory space and then restart the process. But this is not easy. So the whole task is like here. So when we are referencing a page, if we see an invalid bit in the page table, so then we are going to send an interruption to the operating system saying that this process needs to wait because one page is not in the memory yet. So this process is going to go to switch from the running state to the wait state. And then so then the operating system is going to be responsible for bringing the page to the physical memory. And once it is once this page is in the memory, then it will set this bit to the operating system is going to set this bit to V, meaning that it's valid, it's already in the memory, and then so restart the execution of the program again, of the process again. So this is how we handle a page fault. So, but the problem is here is that let's say that when we are visiting a page with the probability P, there is going to be a page fault. So P is a value between 0 and 1. Okay, so and then the effective access time is this. Okay, so because with one probability of 1 minus P, we don't have any page fault. We just need to access the page from the memory directly. So then, so the time is named MA, meaning the memory access time. Whereas, so if in case there is a page fault, then we need to multiply it with the page fault service time. So, but in practice, the page fault service time is much larger. It is significantly larger than the memory access time, because so memory access is faster with page fault. If there is a page fault, we have to load a page. We have to read something from the hard drive, which is much slower. So here is one example. Suppose the one memory access can be finished in 200 nanoseconds, whereas the page fault service time is as large as 80 milliseconds. So here I need to let you know that 1 millisecond is equivalent to 1000 nanoseconds. Okay, so 1 ms is equal to 1000 nanoseconds. So then the total, if the effective access time is here, this is the equation. So So oh sorry, this is not 1000, it's 1 million, it's 1 million nanoseconds. Okay, so then the total effective access time is 200 plus 7, 800 times p nanoseconds. So here we can say that since p is an integer, is a number from between 0 and 1, we definitely want p to be as close to 0 as possible, because if if p is 0, then the effective access time is really small. It is just 200 nanoseconds. Whereas if p is 1, so this number is going to be as large as 8 million nanoseconds. So we want this number to be as slow as possible. So that's why we want the page fault rate, the probability of a page fault, to be as small as possible, as close to 0 as possible. And so so to do that, then we need a good paging algorithm. So let me so for now we need a very good page replacement algorithm. So for now I'm just going to skip copy on write, and whereas I'm going to talk about mainly focus on the page replacement algorithms. So here is an example. Suppose we got two users who are executing, each of them is executing a process. So for the first process, that is executed by user 1. So this process has 4 pages in the virtual memory space, whereas the second process also has 4 pages in the virtual memory space. So this is the picture which shows the physical memory space. So now the physical memory space is full, it's almost full. So we have the first process executing a command, that is to load M, whereas M is still in the hard drive. So our task is to bring in M, into the physical memory. However, for now the physical memory is already full, there is no free space. So what we need to do is, here we got 3 different options. So the first option is that we just terminate process 1, because process 1 needs to have a file loaded or something loaded into memory, but we don't have sufficient physical memory space. And so then the first option is to terminate the current process. But this is not going to be fair for the first user, because suppose that you are just executing a command on a computer which you share with your friend, and suddenly your process or your application is terminated, and then you will be really frustrated. So another option is that we terminate another process. We terminate this process so that we can free some spaces that are occupied by this one, by this process. So we got this one freed, and this one freed, and then this one freed. These 3 pages freed in our physical memory. Then so that we will be able to load the page M into the physical memory. But it's not going to be fair to the user who is executing that process. The only other option is that we need to swap a page out, and then swap the page that we want to load in. So this is called a page replacement. So if we just swap a page out and swap a page in, that is called page replacement. This is pretty much like this. Okay, so suppose here our classroom, so with COVID, our classroom only allows, let's say, 10 people to sit in a class at most. So now I got a lot of students, I got 30 students. So who want to who want to come to the class. And for now, so for some day, if I say, okay, only 10 students can come, but I got 11 students come. So here I got all the seats used by the students, but with one more student standing outside the classroom. So over here, what I need to do is that I need to decide which student to go out so that we can bring this student in. So this is called a page replacement. And then so in case of a page replacement, there is going to be two page transfers. The first page transfer is that, so after we pick the victim page. The victim page is the page in the physical memory that needs to be swapped out. So we just swap this one out. So we copy the content of the victim page to the hard drive. This is hard drive. And then so next we just copy the page from the hard drive to copy the content of the desired page from the hard drive to the physical memory space, to the physical memory. So there are two page swaps or page transfers between memory and disk. So to reduce the amount of page transfer, what we can do is to set the modified bit associated with each virtual page. So the idea is that we're only going to copy this victim page back to its hard drive only if we have modified the content in this page, because if we don't, then there is a copy, the original copy of this page in the hard drive. So there is no need for us to write exactly the same thing again at the exact same space. So which causes a waste of time. That's why we are going to associate each page with a modified bit. If we set modified bit as 1, it means that this page has been modified since we load it into memory. Otherwise, so it is going to be 0. So we're only going to copy the page from memory to hard drive if the modified bit is 1. Okay, so then the overall page replacement procedure is as follows. So first we're going to find a free. So first we find the location of the desired page on the hard drive, and then we are going to find a free frame. So free frame meaning that a frame that is not being used in the physical memory, or a page that is not being used in the physical memory. If there is a free frame, we are going to use it. So it's like if there is an available seat in the classroom, we are going to let the new student sit in that space. Whereas if there is no free space, then we're going to have to decide, okay, which one to go out. So we're going to use a page replacement algorithm to decide which one is going to go out. So then after that, we're going to bring the desired page into the free frame, the newly frame, the free frame, and then update the page and frame tables. So over here we can see that an important task is to pick a victim page, and then we're going to have a page replacement algorithm to do that for us. And now I'm going to talk about the page replacement algorithms, which is the main focus of our lecture today. So the first page replacement algorithm is called first in, first out. So that is that we associate each page with the time at which it was loaded into the physical memory. So in case that we need to invite someone out, we're going to invite the one who comes to the physical memory first out, because it has already sit in the physical memory for the longest time. So this is, if you remember, the first come first serve process scheduling algorithm. You can see that this is just totally opposite to that one. So here I'm just using an example. Suppose that we have a physical memory with 3 frames. We have physical memory with 3 frames available, and then this is the reference stream. So the reference stream meaning that the sequence of pages that we're going to refer to. So in the beginning, our physical memory space is free. So it's all 3 frames in our physical memory are available. So then first, when we are referencing the page 7, we're going to so nothing is in the memory, so we're going to say a page fault. So then we're going to load 7 into the physical frame, and then we're going to refer to 0 to the page 0, but the page 0 is not in the physical memory, so there is another page fault, so we're going to bring 0 in. Now we have 7 and 0, and next we're going to refer to the page with whose index is 1. It's not in the physical memory, so we're going to have a page fault and then bring it in. So, and then we're going to refer we want to access page the virtual page with number 2. So it's not in the physical memory, but at this time there is no free frame in the physical memory, so we have to swap something out, and then we're going to swap 7 out because 7 enters the physical memory first, so we're going to swap 7 out and then swap 2 in. So here is this one, and then we're going to refer the page whose index is 0. So for now, here we can see 0 is already in the physical memory, so there is no page fault. And then we're going to refer to the physical memory, so the virtual memory whose index is 3. So 3 is not in the physical memory, but there is no free space, no free frame. So we're going to pick 1 to be removed. That is, the victim page is going to be the page 0, because among 2, 0, and 1, 0 enters the physical space first. So we're going to remove it and then bring 3 in. Okay, so if you continue this process, you'll be able to get this. And here in total, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. In total, we got 17 page faults. Okay, so, and this is the first in, first out algorithm. And then the second algorithm that we need to learn is named optimal. So because it has the name optimal because it yields the lowest page fault rate. So in theory, this is the best one. So the idea is that we're going to replace the page that will not be used for the longest period of time. So again, let's start from here. Okay, so first we got 3701 in the physical memory, and then we want to load the page 2 in, but now there is no free frame. So we need to decide which now the memory has 7, 0, and 1 in it. So we need to decide which one to be swapped out. So here, to pick which one to be swapped out, we're going to say which one is not going to be used for the longest time. So starting from here, the next time that we're going to refer to the page 7 is right over here, is here, whereas the time that we're going to refer to page 0 is here, and the next time that we're going to refer to the page 1 is here. So 7 is not going to be among the 3 pages. 7 is not going to be used for the longest time. So we are going to swap 7 out and bring 2 in. So that's why we got this. And then we want to refer to the page 0. 0 is already in the memory, so there is no page fault. Next, we want to refer to the page 3, and then there is a page fault. So among these 3, we need to decide which one is not going to be used for the longest time. Okay, so we're going to refer to 2 over here, and 0 over here and 1 over here. So 1 is not going to be used for the longest time. So we're going to pick 1 as the victim page, and then swap it out, bring 3 in. That's why we got 2, 0, and 3. And next we're going to refer to 3. So we're going to refer to the page 0. It's already in the physical memory, so no page fault. Next we're going to refer to 4, okay? So far we got 2, 0, and 3 in the physical memory. We're going to say which one is not going to be used for the longest time. So 2 is going to be referred to here, 0 is going to be referred to here, and 3 is going to be referred to here. So 0 is not going to be used for the longest time. So we're going to swap 0 out and then bring 4 in. So that's why we got 2, 4, 3. If you continue this process, you will be able to derive this sequence. So with the optimal page replacement algorithm, for this example, we got in total 1, 2, 3, 4, 5, 6, 7, 8, 9 page faults. So 9 page faults, which is significantly smaller than 17. So here we need to emphasize that even though optimal is the best one in theory, it's not going to be practical, because in practice we don't know which pages are we going to refer to in the future. So this is very similar to the shortest job first process scheduling algorithm. And then the next algorithm is called least recently used. So for this algorithm, the idea is that the page access pattern for a process is going to remain stable. So for each page, we can infer, okay, the time. So let's say, so now if we have a page in the physical memory, if the last time we referred to it was like 10 minutes ago, then we guess that the next time that we're going to refer to this page is probably again 10 minutes ago. So because our assumption is that the page access pattern is going to be stable. So here the idea of it is that we're going to associate each page with a time that indicates when this page was used last time. So then we swap out the page that has not been used for the longest time. This is the idea. So again, we start from here because the first 3 page access will be 3 page faults, and then we refer to the page 2. Okay, so now there is a page fault, so we need to decide which one is the victim. So 7 is referred among these 3 pages. 7 is referred to here, and 0 is referred to here, and 1 is referred to here. So 7 is 7. Was not used for the longest time. So it's not used for the longest time. So we are going to swap 7 out and then bring 2 in. So that's why we have this. And then we are going to refer to page 0, no page fault, page 3, page fault. So we're going to say which one is not referred for the longest time. So 2 is referred here, 0 is referred to here, and 1 is referred to here. So 1 is not used for the longest time. So then we're going to swap 1 out and then bring 3 in. And then next 0, yes, no page fault. And then 4, okay? So among these 3 pages, we need to decide which one to swap out. 0 is used here, 3 is used here, and then 2 is used here. So 2 is not used for the longest time. So we're going to swap 2 out and then bring 4 in. So that's why we got 4, 0, and 3. And if you continue this example, you should be able to derive this sequence. So this is the least recently used page replacement algorithm. And so this one is used most frequently in modern operating systems, because we can use the data structure of a stack to help us to efficiently find which one should be swapped out first. And then there is the second chance algorithm. So the idea is that we associate each page with a reference bit. So initially we set all the reference bit to 0. If within a certain amount of time a page is referred, we set its reference bit as 1. And then when a page, so when we want to swap a page out, we are going to do this. Okay, if its page reference bit is 0, we swapped out. If its reference bit is 1, then we want to give it another chance because it has been used recently, and our expectation is that it's highly likely it's also going to be used in the near future. So then we want to keep it in the memory, so that because it's going to be used for in the near future. So that's why we give the second chance by setting the reference bit to 0. So this is the second chance algorithm, but in reality it's not that it's not very popular. Okay, so then there are some other page replacement algorithms like least frequently used and most frequently used, which we're going to skip in our lecture. So the next concept is so for frame allocation, we can just ignore it because it's not going to be. So this is just too it's too much for us. So we are going to skip that. But a very important concept that we need to know is named thrashing. Thrashing means that if a process does not have sufficient space, sufficient pages, then the page fault rate is going to be very high because, say for example, if the reference bit of a process is 0, 1, 2, 3, 4, and again 0, 1, 2, 3. Okay, so here if we only allocate two frames to this process, so over here we got 0 and 1, and then we just load 2 in, and then load 3 in, then we load 3 in. So the problem is that we keep getting page faults because the number of page frames of the number of frames for this process is too small, so that the pages that we load into physical memory are not going to be used in the near future, and so that we keep getting page faults, and this process is going to be stuck in swapping pages in and swapping pages out. So it's going to be extremely slow. This process is going to be extremely slow to execute, and this is why that okay. So when you are picking computers, I would definitely say nowadays, say if you want to get a new computer, no matter if it's a laptop or desktop, make sure that it has at least 16 gigabytes of memory, because if your memory space is too small, you are going to get into thrashing, and you're going to be really mad at the performance of your computer. Okay, so here we just need to know what is thrashing. Thrashing is because that the number of frames for a page is too small. And at last, we need to know a technique named memory mapping. So what is memory mapping? So the memory mapping is like this. Okay, suppose that we have a hard drive over here. This is our hard drive, and then we have a file. Let's say F is a file. So usually this file is stored in the hard drive. So if we want to access this file, we need to use the function called read, which help us to load this file into the memory. And then if we want to write something into the file, then we need to call the function write, which writes something into the file on the hard drive. So everything is operated on the hard drive. But with memory mapping, what we can do is that we just directly, it's like we create a mapping between, so we allocate a certain space in our physical memory to this file. So we we create a mapping between this file and this memory space. So then if we just, so in order for us to read something from the so from this file, just need to directly read from this region of the physical memory. If we want to write something into the file, just need to directly write something into this region of the memory. So because there is a mapping, so between them, and this is called memory mapping. So here this is the technique that I'm talking about. Create a mapping between two. So and with memory mapping, we can let different different process share the same space. And the system call that allows us to create mapping between a certain memory space and a file is named mmap, meaning memory map. So the utility is to allocate a memory or files or device into memory. Okay, so it takes the parameter of the address of the memory. So it's like which part do you want to use as the mapping, and then the size of it. So how large space do you want to allocate, and then the other thing is that the FD meaning file descriptor or the file identifier. So which tells the operating system, okay, so which file do you want to map to this space? Do you want to map to this space? So here I have an example over here. I prepare a code example for you. So okay, so first in this code example, we open a file whose name is mmap, is mmap.c. So the file path is mmap.c, which is just this program. So this program is stored in a file named mmap.c. So here we first open this file and then get the identifier of this file, meaning that we just get the ID of this file, and then we create a mapping between a certain space. So it's between the memory space, whose starting address is 0, and we create we allocate file size, meaning that how large is your file. So we we allocate sufficient size of the memory space to this file, and then we create a mapping between this memory space and then with this file. So if it's successful, we are going to directly print out a message, which is the content in the file printed out. Okay, so here to print it out, we are not using a read. We're not using the read function. We're just using print. Okay, so this is if we compile it and then execute the program. This is what we're going to say. It's going to print out every line, all the lines of this file in your console or in your terminal. So with memory mapping, we're able to directly read and write from memory rather than hard drive. Okay, so this is our content today. The most important one is named is the page replacement algorithms, and then you are going to have your second homework on this topic. The second homework is going to be due on December 11th, which is the Friday. Okay, so the level of difficulty for homework 2 is pretty much like homework 1, and also so we learned 2 topics named thrashing and memory map files. Okay, so this is our content today, so thank you.